As you can remember from the previous class, we were talking about the different types of failure criteria. And I only talked about in detail the two criteria which are commonly used for metals, or which could be used for in metals. Then there are some other criteria which can be used in different materials. So for example, for soil and concrete, the Tucker-Prager model and Moore-Coulomb model, these are more commonly used. There are some other models also. Maximum principal stress failure criteria and so on. Those things you can find out. So depending on which kind of material you are dealing with. So for example, the materials which are very, very brittle, there sometimes it depends purely on the tensile stress. So such kind of materials, there are some other models that are commonly used. I'm not going to go into all those models, but if you are interested, you can always find a lot of literature even online, and there are plenty of books available on mechanics and elasticity, plasticity. And I'm sure most of these models will be taught again in elasticity, plasticity in a more mathematical way. The way I have taught it to you, it was more physical, so that you can use it better as a designer. You have a physical feeling of it. But when it is taught in elasticity, plasticity, it will be done from more from mathematical formulation point of view. But I hope whatever explanation I have given here allows you to correlate the two. Okay, then we were talking about this different types of IS Indian standard sections, beam sections, and in addition to the beam sections, that these are your ISJB, your ISJB, LB, MB, HB sections. These are junior, light, medium, and heavyweight. Then you also have a wide flange section. So wide flange sections are slightly wider than ISMB sections. So ISMB sections we saw had a ratio of approximately 1:2. ISWB have slightly higher ratio of D by B ratio. Okay, so sorry, or B by D ratio. And ISSC almost have equal B and D values. Okay, so both of these can be very easily used as columns, ISWB and ISSC. In addition to these, there is also a completely different category of parallel flange beams. Okay, and last time I was somewhere here when we stopped. So parallel flange beams have a distinct advantage. I think we were discussing this and we stopped somewhere along the way. So regular I sections typically have flanges which look like this. Correct? And again, the drawing is not very easy. So what we see here is that even in this portion where the toe and the fillet, this part is the fillet, you can note it down. It is called fillet. And this part is called toe. Okay. Even the part that is in between the toe and the fillet, that is supposed to be kind of a not disturbed by these curvatures, sharp curvatures at the toe and the fillet. Even this portion does not have a uniform thickness. It actually, if you look closely, it has this kind of a varying thickness. Okay, of course, it is exaggerated here. Now, the challenge with this kind of an approach is, this kind of a section is that if, let's say, I want to put some kind of a bolted or rivet or some kind of a connection here, then what happens is that this is one plate to which I want to connect this particular flange. Okay. Now, what I would do is I'll drill holes in the two plates. One is the flange and the other one is this plate. And then I'll try to put a bolt here. And when I put a bolt here, the bolt head will be sitting. So on this side, there will be a nut maybe. So one of these will be the nut. The other one can be nut also, but I'm assuming that that is nut and this one is bolt head. Fine. So what will happen is that because of this bolt head wants to sit on this surface, and this surface is not aligned properly with the bolt head, and there is this gap that you can see here, right? And that gap will cause an uneven stress distribution on the bolt head. As a result, the bolt has to bend, or the bolt head will have to undergo a non-uniform kind of stresses, and tightening the bolt becomes very difficult in this situation. You can see the screen, right? You can see the drawing. Please confirm.
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir. Yes,
So
sir.
you can appreciate the issue here, right? So there are various ways in which you can compensate for it. There are different types of filler plates or washers kind of a things which have this kind of a tapered section, okay, which can compensate for it. So you put one such plate here which will fill this space exactly, so that you have a perfectly parallel surfaces available at both ends. But that is additional material that you have to keep account of, okay. And also it's not a very elegant design. The major advantage that parallel flanges bring in is in this respect. So of course, near the fillet and near the toe, you will have a sharp curvature. But at least away from the fillet and away from the toe, you have a very nice flat surface which is parallel to the other face. Okay. So in this particular situation, you don't have to use any other material as a filler plate or washer or something. I mean, of course, you can use a washer if you need to, but that is not really required because of the geometrical issues. Okay. So you don't need a tapered kind of a washer or tapered filler plate. So that is the major advantage with parallel flange beams. Then within parallel flange beams, you can have a narrow beam, you can have a wide beam, and you can have beams which can be used for columns or piles and so on. Right. So even for piles, we prefer to have the basically what happens is that as your beam becomes wider and wider, so you may have a narrow beam which is basically almost this ratio, width to depth ratio will be almost this 1:2, right? Alternatively, you can have a slightly wider beam where the width to depth ratio is slightly higher. And in such kind of a beam, you have, of course, the bending moment capacity against this kind of a moment is higher. In this case, the bending moment capacity in this moment was much higher than the bending moment capacity against this moment, correct? But in this particular case, the bending moment capacity against this moment, if I call it mx, let's say, and I call it my, so the capacity or stiffness in the two directions, they are not that farther off. So in this particular case, they are very different. So oftentimes you can see that this moment capacity will be almost 8 times or 6 times higher than this moment capacity. Same thing with the stiffness. But in this case, it will not be that different. And that may often be desirable depending on the application. So when you are dealing with a beam where you are going to use it as a beam, of course, this is a more desirable behavior, because why do you want to waste material by providing it more flexural rigidity in the minor axis? You are not going to use it in the minor axis so much. But if you are using it as a column or as a pile, then there are issues of buckling and so on. And you want for a pile, you need a greater surface area to develop more friction. And for all those reasons, you may require a decent amount of width. Then you may have channel sections, again, junior, light, medium, and medium parallel flange channel sections. Also angles. So these are also available. Most of the angle sections that are Indian standard angles are available in IS 808 also. And also the textbook, Subramaniam's textbook, also provides you some details of these cross sections. And I'm sure you have seen these tables. So I'm not showing you a picture of each one of them. You can find them. Then similarly, T sections are also available. T sections typically look like this. So T sections also have a flange and they have a web as well. So just like in any I section, you have a thinner web and thicker flange. Okay. Now, this kind of etc. Okay. Then there are some variations of this one, and then there are plates, flats, and bars, which are basically simplest geometries. So plates, they are called plates if the thickness is more than 5 mm. Sorry, thickness should be less than 5 mm. That is a mistake here. So plate should have a thickness of 5 mm with thickness. No, more than 5 mm. Sorry, yeah. And if it is a flat, the thickness should be more than 5 mm, but the width should be less than 250. If the width is more than 250, then it comes as a plate. It is called a plate. So if the width is less than 250, and that's how it is rolled, not by cutting a plate. If you cut a plate to make it 250, then you don't call it a flat. But the flat should be rolled that way. So if it is less than 250, then you call it a flat. And then bars are typically square or round. So you will often see the use of plates or flats. I have never really seen much used. You can see plates often in the industry, and you can see bars often being used. These sections are also relatively uncommon. Angles, channels, and eye sections are much more common. Okay. Then there is something called residual stresses. These are also very important cross-section properties or cross-section characteristics, which we should be aware of, and we have to often design for them. And these become very critical when we deal with compression members. In tension members, they are not so important, and we will discuss why. And I think we will discuss that when we discuss compression members. Okay, I'll not discuss. I'll first talk about tension members starting today's lecture. But since these don't play a role, I'll not even talk about why they don't play a role. Okay. So what are residual stresses? These are locked-in stresses due to uneven heating and cooling during the manufacturing process. Okay, so it seems straightforward, but if you try to visualize, it becomes slightly complex. So for example, these are the two pictures of built-up sections. Similarly, you may have an eye section also. So let's say this is the rolled eye section, hot rolled section. Geometry is not perfectly shown, but you may have a fillet here where the thickness of the web increases suddenly. Okay, and in this kind of a situation, what happens is that when the cross section comes out of the furnace, it is all uniformly hot, very hot. Okay, and then as it starts going through the rolling process, some portions become thinner and thinner. So the web becomes very thin. The flange corners, they are thinner. Plus also what happens is that they have a larger surface area for the unit mass. So for a given cross section area, the corners of the flange has larger surface area. Whereas in this portion, if you see, for the given cross-section area, you have a very little surface area. If I may draw it again, just to elaborate further. So if I am drawing the junction between the flange and the web, and I take a portion here, right? You can appreciate, right? This is the web. The web is extending this way, and this is how the flanges are extending, top and bottom. So if I take this cross section, for this much of cross section area, how much of exposed area do I have? So you have this much of exposed area, you have this much of exposed area, and you have this much of exposed area. And these two areas are not exposed. Similar thing is true for the flange ends. For this much of cross section, you have this much of exposed area. Sorry, not same thing is true. Opposite is true for the ends. So what you see here is that either the thickness is high, or because there is a corner, and because of that you get a larger surface area. So where your surface area to the cross section area ratio, or surface area to the mass ratio, becomes high, those portions start to cool down quickly. In the middle of the web, for example, if you look at it, you got this much of cross section area, and you got this surface area. So again, in these locations, since the thickness is very little, you get much larger surface area. Similarly, large surface area here, large surface area here, and very low surface area per unit volume, per unit mass. Okay, whereas these will have high surface area per unit mass. So these portions cool down quickly. and this portion does not cool down quickly enough because there is more chunk of mass sitting there. So these areas don't cool down fast enough, and these portions cool down fast. Okay, and when this cooling is happening, at the time when this cooling down is happening, the same time the steel is also solidifying. Okay, so as a result, what happens is that this portion is still hot, and then steel is also gaining strength. Okay, so at that time, let's say this steel becomes much cooler, and this is still hot, and the shape is finalized. Now what happens is that subsequently, when this steel also starts to cool down, now it wants to shrink. This steel wants to shrink, but this steel, which is at a much lower temperature, does not want to shrink with it, right? Because this is solidified. So as a result, what happens is that you end up developing a tension force in these parts. Okay, so when you are developing tension here, to balance that, you have to develop a compression here. In essence, what is happening is that this portion is pulling the rest of the cross section in, and the rest of the cross section is pulling the middle portion out. You understand? So if I may, let's say, try to draw on this slide itself. Okay, so let's say this is the flange I'm looking at, and these are the different locations. So what will happen is that this portion will be in compression, and this portion will be in tension. So that is this portion of the flange. At this surface, it will be pulled into this, and there it will be pulled like that by the rest of the beam, the rest of the flange. And this one is pulling the other way. Okay, I don't know whether these images were very clear or not, because this might have confused you further. So essentially what happens is that you get a lot of tension in this region. Tensile stresses, and you get a lot of compression in these regions. Okay. Fine. It has been observed for typical cross sections, depending on what type of thicknesses you have in the member. If you have thicker sections, then you are more likely to have higher residual stresses. As you can understand, if your cross section is thicker, then you will have more mass sitting here for the given cross section, for the given surface area, from where you lose the heat. Okay, so if you have more mass sitting here, you will have higher level of residual stresses. But typical ISMB or IS LV sections, you may have maximum tensile stresses of up to 30% of Fy and maximum compressive stresses of up to 50% of Fy. Why? Because here you may have very high compressive stresses at the corners, and the distribution of the stresses here, it is shown as almost like a parabola, but you may have various other distributions, and a lot of data is available in the literature where you can find different types of distribution. Often we assume the distribution to be, for easiness of calculation, sometimes we assume the distribution to be this way, linear. Okay, so this is right in the middle. So half of the cross section is in compression, and half of the cross section is in tension, and maximum compression is equal to maximum tension, something like that. What you have to make sure is that total compressive force in the cross section has to match the total tensile force, right? Why?
Because they are self-equilibrating.
Why?
They are because no external load is acting, no, sir. I mean,
exactly. So yeah, very good. So the cross section, these stresses that I'm talking about, they will be acting within a member on its own. So I don't have to apply any force on the member to introduce these stresses. So if I take a beam, let's say 2 meter long beam, And anywhere, if I can find out what the stresses are, and it's not easy to find out stresses or measure stresses, what you can measure are strains. But anyway, if you could, there was, let's say, a hypothetical way to calculate stresses or measure stresses, you would see that stresses are present in this fashion, the fashion that I had shown you, this tension compression variation, even without you applying any load from outside. And the two forces, and in order to for the cross section to remain in equilibrium, the two stresses have to balance each other out. So total compressive force has to be equal to total tensile force. Okay.
So can you explain once more why there are compression at the edges and tension in between? I'm totally
sure. So yeah, that part is important. So you should be able to follow it. See, what happens is that this part, that part that is in the part that is in tension, or I'm marking that as tension. This part cools down later, right? That part is clear, and this will cool down first. The blue part will cool down first. Is that much clear?
Yes, sir. Yes, sir.
So since this part has cooled down already, this has already shrunk whatever it had to shrink. Okay. So when it is cooling down, it will shrink during the cooling process. But at that time, this portion is much hotter, and it is very happy to shrink along with the blue part. So when the beam is cooling down, the entire beam is shrinking. Don't you think it should shrink? Why should it shrink, or it should not shrink?
Yes, sir. It will.
It will, when things cool down, especially steel, when it cools down, it shrinks. It has that thermal expansion, right? We had talked about thermal expansion. So when it is cooling down, the entire beam is shrinking. And in the beginning, when this blue part wants to shrink, and the red part is not cooling down at the time, and it doesn't want to shrink, but the blue part wants to shrink, blue part is at a lower temperature. That means it is stronger. And red part is at a higher temperature. That means it is weaker. So blue part wants to shrink. It will make the red part shrink along with it, and red part will be plastic at that time because it is at a higher temperature. So it will shrink and it will deform plastically, which will not introduce stresses in the beam. Okay, so that part is done. You got initial part cooling. These blue parts cooled already. Okay, and now they have solidified. They have become harder now. They are stronger. And your red part is still hot and it is soft. Now slowly, and at the time there are no stresses because this red part was not able to offer any resistance when the blue part was shrinking. Fine. So there are no stresses. So there are plastic deformations, but no stresses. But now what happens is that now the red part wants to cool down, and the blue part has already cooled. It has already become strong. Now the red part wants to shrink. But now the blue part says, okay, I'm done. I have had my lunch. I'm not going to pay for you. Okay. So then the blue part says, okay, I've already gained my strength. I'm not going to just follow you just because you want to shrink. I don't give a damn. You manage. So the red part, now when it wants to shrink, it cannot shrink because the blue part is holding it back and it has already solidified. So it will try to shrink, and in the process, it will develop a tensile strain, right? You remember that, right? So imagine that these are two different members. So red part is one member and it is cooling down now and it wants to shrink. It wants to shrink, but the blue parts on both sides are not letting it shrink because they are also bonded with it, right? They are part of the same member. So they will not let it shrink, and as a result, the red part will develop some kind of a, imagine that I'm holding one rope on each side and I want to shrink. But what kind of stress will I develop if the ropes don't let me shrink or ropes don't let me contract? I'll develop tension. So the red part, the part that is marked as red, will develop tension, and in the process, the blue part will develop compression because it is the one that is not allowing it to shrink. So the red says, okay, let's develop some stresses. I'm going to shrink anyway. At least I'll try to. And in the process, I will develop some tension. You will develop some compression. Okay. So now the relationship becomes a little bit strained, but that's okay. That's how they like to live. Is that clear? Did this explain a little bit, Manik?
Yes, sir. Yes, sir. Thank you.
Okay. Good. So the same thing. And of course, they have to balance each other because that force is not coming from outside. That force, red part is applying on the blue part. So the two have to manage between them. Okay, so the two forces have to balance. So total compression has to be equal to total tension. But maximum compression need not be equal to maximum tension, that depends on the way it is distributed. If it is distributed like this, then this compression force may be higher than tension force. If it is distributed like this, then maybe the maximum values are also same. Similar kind of thing happens in welded sections. So you have one plate here, you have another plate here, you have another plate here, and these two plates you are welding using two fillet welds or maybe one groove weld or whatever. Then when you weld them, at that time, this portion of the beam or the cross section was cold, and it was cold. It was never heated. But this portion will become hot. Okay, but it will become hot at the same time. It will plasticize while it is becoming hot, because you have to clamp it to make sure that it does not distort. Okay, so it has plasticized, and now the two are of equal length, but this one is hot. This portion is hot, but the two are of equal length because initially it plasticized. Now when it wants to cool down, what will happen? Again, it will want to shrink, and this won't let it shrink. And as a result, you will have a stress distribution developing, stresses developing like this. Now, the typical stress distribution in case of a welded section has a much more severe concentration or severe steep change in the stress values. And that is obviously because your heating is very concentrated. When you weld it, you heat it only locally. You don't heat the entire section, unlike here. So your stresses will be relatively more concentrated in this area. Okay, but they exist nevertheless. And there are ways to release these stresses, residual stresses. There are some mechanical methods. There are different types of hammering, or there are various ways. You heat it and hammer it slightly so that you can release these residual stresses, especially if you have there are some types of cross sections which are known as jumbo sections. In India, I don't know what they are called, via HB maybe. So basically, when the flanges become almost 100 mm thick, in such kind of cross sections, the residual stresses can be very high, up to 70% of the yield stress. And when the residual stresses become that high, that becomes a major concern when you design. Okay, because you are almost already at 70% of the yield capacity. What more can you use? You can use only 30% more, right? So that becomes a concern, and there are ways to release those stresses, especially after welding. There are ways to release the residual stresses. I'm not going to go into that one. If you want to take some courses on fabrication, maybe in the materials or mechanical engineering, there you may find more details. Okay. So, but you don't have any issue of residual stresses when you go for this kind of a built-up section, which has bolts. Bolts don't have an issue of residual stresses. Okay, so residual stresses are already logged inside the member, and when you design a member, you have to worry about these stresses because these are already present stresses. On top of them, you are going to apply some external stresses, and at that time you have to plan accordingly. Okay, so concluding the discussion on residual stresses, any questions?
Sir, I mean, those residual stresses will be acting along the width, no, sir?
From the length.
Along the length. Means,
Yes.
sir, but the variation is along the width, no, sir?
Variation is along the width. Yes. So let's say you have a member, and that let me try to draw it. I don't know how will I. So let's say you have a plate here, which was a flange. Okay, or let's say it is still a flange. So what will happen is that, as I mentioned, the different portions will have different level of stresses. Okay, so let's say in the middle you will have tension. Tension is this kind of a stress.
Yes.
And here at the ends you will have compression. Similarly, here you will have compression. Here you will have tension, and here you will have compression. Yeah, and something in between here. Okay, so likewise, so the distribution is in the width direction, but the stresses work in the longitudinal direction. And actually, how do you measure this is also very easy. Basically, what you do is you take a beam. You see, this is the beam. You have a long beam, whatever, like 2 meters, 5 meters, whatever. Then what you can do is you can attach some strain gauges to this. Along the strain gauges should be oriented along the length, but they should be placed in the width direction, like, you understand, right? So this is the width direction. So you put at the same location in the width direction. 1, 2, 3, 4, 5, 6, several of them you can put. Then what you do is, when you cut strips from this in such a way so that each strip gets one strain gauge. Okay, and let's say you had set the initial strain gauge strain value as 0. After you cut them, you will see that those strain gauges develop some strain. Okay, so now you cut that strip. Now you got this standalone strip that is cut from this beam, and now the strain gauge has got some strain in it. Earlier it was 0, now it has got some kind of strain. Okay, what does that mean? Now, of course, you are sure that there are no stresses acting because I've cut a very thin strip and I'm not applying any stress from outside. So there are 0 stresses on this. That means there were some stresses here which got released when you cut it. Okay, and by measuring how much strain you get from when you change from here to here in the strain gauge, you can back calculate how much stress was there at that time. Because if the strain here is 0, stress was whatever, you get a strain which is non-zero, get certain strain, but you know that stress is 0. Okay, so you know that your stress is 0, and here your strain was 0 because that's how you set your strain gauge as. So whatever change in strain happened, that would mean that there was some stress here. Okay, got it, Lohit?
Yes, sir. Yes.
Okay. So now we will move to the next topic, that is design philosophies. Okay, so let me take you to a small number line. Let's say I have a number line, okay, and on this number line I am recording different force values and resistance values. So the way it is done is, this is increasing order. So if I'm marking on a structure, or let's say on a structural member, what is the load and what is the resistance or capacity. Okay, so let's say I mark load here, and this is the increasing order. In this direction the numbers are increasing, and my resistance is here. So this is Q is the load and R is the resistance. Then is this structure safe? Is it safe or not?
Yes, sir.
Yes.
Yes, sir.
It means it is safe. So R divided by Q is greater than 1. Okay. On the other hand, if I had Q here, sorry, if I had R here and Q here, then what it would mean? Unsafe. Fine. That is obvious, right? There is no mystery here. If your load demands are greater than the resistance or the capacity, so R is resistance or capacity and Q is load. So of course then it is unsafe, no mystery. Now what happens is that, how do I know how much load actually is acting? So there are ways to calculate the loads. And how do I know how much resistance the structure has? Then there are ways to calculate the resistance or the capacities. Right? So let's say I want my structure to be safe. I don't want it to be unsafe. So I design it in such a way that my R, that is R design or R nominal you can call, that is the capacity I want, is greater than my Q that I estimated. So you can say R estimate is greater than my Q estimate. Okay, of course I have to design it this way in order to be safe. Okay, agreed? But the real life challenges are that my R estimate may not be actually the real estimate, real R. That may be my estimate. That's what I want it to be. But my real life does not work that way. So even though I design, let's say I have a column and I estimate the column capacity to be 100 kilonewton based on whatever understanding of the column behavior I have and a lot of lab tests I can do. But in spite of all that, the column that I actually have in the field may not actually have that much of capacity. Okay. So then what may happen is that if I test, let's say 100 columns, for which all of those 100 columns, I had estimated the capacity to be this much, exactly this R estimate. They are identical columns or identical type of columns or whatever, like, so even with those columns, what will happen is that majority of them, if my understanding of the behavior is correct, majority of them will be showing me this much of capacity. Okay, but there will be some which will be showing me slightly less capacity, and there will be some which will be showing me slightly higher capacity. And if I test large enough number of such columns, study the behavior of large enough number of such columns, this is frequency. Okay, if I study the behavior of large enough numbers, then I can draw it as a frequency versus measured values plot. Okay, so if on the vertical axis I'm plotting the frequency, so maybe out of 100, some 20 will be within plus minus 5% of this value, and then some 15 will be plus minus 10% of that value, then and so on. And that's how this actual distribution will be. Fine. And here, the way I've plotted this plot, it looks like a normal distribution. That's how most of the member or material behavior plots do follow this trend, but that is not a universal truth. It looks like a normal distribution here, but it need not always be normal distribution. You understand? So if I test a large number of such columns, which for those columns I had estimated the capacity to be this particular value, the real capacities may be different. It may be here, it may be here, it may be here, it may be here, but the chances of deviating away from this value will be smaller as you deviate away more and more from here. Everybody agrees with this? You must have all seen these plots, right? Normal distribution. The highest probability will be, if my understanding of this behavior is correct, the highest probability will be in this area. Okay. Now, similar thing can be said about the loads. So, for example, let's say I'm working with the dead load. So, I know the density of concrete, I know the density of steel. So, I can calculate the dead weight of building with a decent accuracy, and I know how much of the dead weight I'm going to get, dead load I'm going to get from a building. Okay. So, but what may happen is that maybe 90% of the buildings will be very close to that value, but still there will be 10% which will be slightly away. Maybe I'll underestimate, maybe I'll overestimate. So, here, 90% the plot should probably go a little higher. Right. So the Q plot will look, Q versus frequency plot will look somewhat like this. Agreed? Fine. So this plot, for example, since I was talking about dead load, I have given a higher peak or a more narrow band in a way, because dead loads are very easy to calculate and we have good enough confidence because we know the density very well, we know geometries very well, so we can calculate these loads very accurately. If it were a wind load, the distribution would have been much wider. Wind load or earthquake load, then the distribution would have been much wider. Okay, shallower and wider. But since this is dead load, we know accurately enough. I'm marking it as a sharper. Fine. So now what happens is that it is not sufficient for me to say that R estimate divided by Q estimate is greater than 1. Need not be safe. You understand? So even if I am making sure that my R estimate is higher than Q estimate, it does not necessarily mean that I am in the safe ground. Why? Because my R estimate is this, but my real R for that particular column that I'm using in a building could be this one with a very low probability, but it may still be there. And my Q, even though Q estimate was this, my real Q may still be here. And as a consequence, my real Q that is coming from this plot may still be higher than my real R, and I may end up with an unsafe system. Agreed? Okay. So now what do I need to do so that I don't end up in this kind of a situation where my real R becomes less than real Q, even though my R estimate was greater than Q estimate? What do I need to do? Anybody? Some suggestions? So if I am going to design a building,
factor of safety, sir.
Sorry, louder.
Factor of safety.
Yeah. So where is the factor of safety in this diagram?
I mean that if there's a ambiguity means then we can give more factor of safety, then it will be
Correct. Yeah. You're right. So we can increase the factor of safety. But if I increase the factor of safety, what happens to this plot?
then R will shift to right side.
Very good. Yes. So what we need to make sure is, basically we need to make sure that because first of all we have to know the distributions, this distribution, how flat or how steep these distributions are. Steeper means we have more confidence, flatter we have less confidence. Okay. So depending on how flat or how steep these distributions are, or how narrow, steep means narrow and flat means wider, broad. So if it is a steeper distribution, then we don't have to separate the Q and R very far away from each other, Q and R estimates. But if we have, let's say, narrow band, flatter bands, then we have to make sure that our R estimate, or you can call it R median. Okay, I'm not, estimate basically was just initially to help you. Basically, that's where your median values will be. And if you know the behavior correctly, then that's where your estimate will be. So I have to basically make sure that my R median is far away from Q median, or sufficiently far, so that the chances of my R being here or my Q being here are as little as is acceptable to me. Fine? Because that's what our purpose is, that our Q real should not be more than R real. So the chances of this happening are as low as possible, or as low as is acceptable to me. Okay. Now what we can do is we can develop mathematically from this point. We already know that I have to make sure that R divided by Q has to be greater than 1. So what I can do is, I can plot, instead of plotting Q and R separately, I can plot a curve which is basically equal to R by Q. Okay. And this I have to do for different R's and different Q's. So R of the column, let's say compression strength of the column, and Q, let's say gravity load. Then separately Q I have to do it for the wind load and so on. Right. So I can do that. And basically, again, that may turn out to be a normal distribution. Okay, somewhat like this, wherein this will be your R by Q median value, that is the most probable value, and this is frequency. Okay, right. Now R by Q will not become 0. So basically what you have to make sure is that here your R by Q should be greater than 1, right? So anywhere where R by Q, let's say this is 1 and this is your median value. So wherever your R by Q becomes less than 1, that is your unsafe zone. Fine. Agreed? This entire thing, that is your unsafe zone. Or I can go a little bit more mathematical and I can take a log. Okay, and I'm assuming that even that distribution remains normal distribution. If R by Q is normal, even ln R by Q will be also normal. So in that case, what will happen is that if R by Q has to be 1, ln R by Q has to be less than, has to be 0 at least. So in that case, this normal distribution, if the value is less than 0, then you are in the unsafe zone. Agreed? So as long as you are on this side, you are safe. Okay? Now, what we have to make sure is that this is that plot. This is the plot I've just shown you. So now here, what we have to make sure is that our plot has the peak which is far away or as far away as we want it to be from this line, that is 0 line. Okay, so yeah, this peak, that is your median value, that's where the peak is far away from this point. And that distance can be called beta, that can be expressed in the terms of beta times sigma. So what will happen is that you have a log normal distribution here. It has a certain sigma. What is the sigma? Standard deviation. So for a normal distribution, one standard deviation basically on each side, if I go, so basically I'm going sigma here from the mean value or median value, then basically I'm including about 68% of the samples. If I go 2 sigma on each side, I think I'm including some 95% of the samples. So probability of 2 sigma is basically making sure that I'm covering almost 90% of them. Okay, so what it means is that if I, this I'll call it sigma, then this distance, this is the edge where the safety is challenged, and this is what I can target, because this is coming from the estimate. Mean is nothing but the estimate. I can estimate the mean, or I can try to achieve that mean, because that's what I test in the lab. Okay, so I can shift my R by Q mean away from this line of safety or the boundary line of the safety by doing what? By fixing this distance, and I can express this distance as a factor beta times the standard deviation sigma, and that standard deviation is the standard deviation of ln R by Q. Okay, so basically all I have to make sure is that what is this value? This value is ln R by Q mean or median. Okay, so I have to make sure that my ln R by Q median, that is this value, is greater than whatever beta value I want to pick multiplied by sigma. Agreed? So if that is the case, I am far away from the, or my probability on this side of probability of being on this side is less if I am far away. So I have to select the beta value. And what is the beta value called? There is a name for this.
Reliability factor.
Yes. So I have to select my beta value in such a way that the probability, this area, there is the probability, right? The probability of failure, that is basically the probability of failure. Is small enough. Okay, and how small is small enough? So there are some values of beta given to you for the normal distribution function. So in a normal distribution function of this kind, if you have a beta of something like 3, then your probability of failure is approximately 0.001. That is one out of 1,000. Okay. And typically in Indian code and international codes also, we usually accept a beta value of something of the order of 2.8 or so, between 2.5 and 3. Okay. So that is the level of risk we are accepting. Now the question is, and that's how, and what do we do when we fix a beta value? Then what happens? Once you fix that beta value, we find out what is the, for that particular beta value, what is the value of, because the beta, and see, sigma we can't change because sigma depends on entirely on the processes. So for example, we are talking about wind load, so it has a particular type of distribution of probability. Similarly, when we are talking about concrete properties or concrete compressive strength, it has a particular distribution. We cannot change that. That's the nature of the players that we are dealing with. So sigma we can't change very much. For that, we have to go to different materials if you want to change sigma. So let's say we have fixed the material, so our sigma is fixed. If you want to use a particular beta, that means I have to increase my R with respect to Q in such a way so that I can get the corresponding level of safety, right? Because beta corresponds to probability of failure. So larger the beta, smaller the probability of failure. So if I want to reduce my probability of failure, I have to increase the value of beta. That means I have to increase the estimated value of R, or median value of R. So I have to push R and Q away from each other. So Q median I cannot change, but R median I can push, right? So I can design the structure to be stronger, or I can put more material, so that, and that is basically the gap between R median and Q median is your factor of safety. This gap is your factor of safety. Okay, so I need to increase my factor of safety in such a way so that I can achieve the beta value, the desired beta value. Is that clear? Now the question comes, even with a value of beta, let's say 2.8 or so, you are, or maybe even 3, we are going to get a failure probability of almost 1. Is that what it should be? I mean, 1 out of 1,000 means if we build 1,000 members, 1 member will fail. But do we see that happening? I mean, every single building has thousands of members, but 1,000 members don't fail, right? Because there is, in addition to this, there are other conservatism built into the design provisions. So for example, when we take concrete strength, we say concrete, this is done on top of, so let's say this is the concrete strength behavior, right? This is the curve, and we do median curve here, right? But when we take concrete strength, we don't take the median value. When we say M30 concrete, what is that strength of M30 concrete? What is the median strength of that concrete? What is that? Sorry?
Median strength may be greater than that character strength.
Yes. So what does the characteristic strength correspond to? Yeah, I mean, the point is valid. Of course, you may not remember the numbers. Yeah, so basically characteristic strength, depending on which material we are dealing with, is the strength below which the probability is only about like 5% or 10%, something like that. So we fix that number somewhere. So again, we, instead of actually taking the median value of the resistance, we already take a very low probability value of the resistance. And therefore, in spite of having a reasonably or a alarmingly high value of failure, I mean, 1:1,000 is also very large amount of failure. Every 1,000 members, 1 member should fail. But then, in addition to that, there is a lot more conservatism built, even at the material level and at the load level. And because of that, the structures turn out to be safe. Okay. Any questions from this so far? Okay, move. Yeah, somebody has a question?
Hello, sir.
Yeah.
So what's the idea behind flattening the curve of Q and R?
Flattening the curve of Q and R. No, see, the thing is that the curve, whether it is flat or whether it is steep or it is narrow, steep or narrow, I'm just using 2 words for the same thing. So either it can be narrow or it can be flat. So when you say it is flat, that means there is much more unpredictability in the behavior. So let's say Q curve is the load curve. So wind load, when we are talking about, okay, so in a particular region, you can say that, okay, in this particular region, maximum wind load is 90 km/h. Okay, but saying that 90 kilometer is the maximum speed or whatever, like this is the wind speed you need to design it for, but the variability of that wind speed is very, very large, right? So even though you have a measurement from last 50 years, the fluctuations in that wind load will be very high. But if you compare that with dead loads, if you say that dead load of this building is, let's say, 2000 ton, okay, then you actually, when you and how do you get at the 2010? You take the measurements, you know the member sizes, you know the slab thickness, you know the amount of steel you have used. From there, you will calculate. And when you actually measure the weight of the building, let's say, you will find that you will be off by maybe 5%, most likely. You will not be off by much. So for such kind of things, you can have a very steep, very narrow kind of a distribution, because if you have 100 such buildings, out of 100 such buildings, you will always get values in that range only, very close to your original estimate. But for a wind load kind of a situation, let's say you have 100 very heavy 1 in 50 years storms. Out of those 100 storms, you will get to see that the variation is so high, even though you are picking one value for the median value, the distribution of those 100 storms will be very high. So let's say you are saying 90 kilometer per hour, but you will see that one storm will be reporting only 50, and another storm will be reporting almost 150 instead of 90. Right? Same thing between, let's say, on the R side, if I'm talking about R curve, R versus frequency. So that is the resistance side. So in steel, let's say somebody sells me a steel of Fe410. Okay. And I get 5 samples of Fe410 from that guy. I test all 4 samples, same diameter, same everything. I test 4 such samples. Chances are that from 4 samples, I will get 411, 412, 419, 409, something like that. Okay, or 412, something like that. The variation will be very little. But if you do a casting of concrete and cast 4 cylinders, identical cylinders, same part of casting, and you test 4 cylinders or 4 cubes, and you are targeting it to be 30, what will happen? What will be the strength? Starting from 24, you will get everything to between 24 and 38 instead of 30, right? So when that happens, then you have a flatter curve. Basically, what is happening is that the probability of deviation from the mean value is also quite substantial. So that's why you are getting a more flatter curve.
Yes, sir.
Did it explain? Yeah.
Yes, sir.
Excuse me, sir.
Yeah.
Sir, can you once more tell about how the beta value is to be taken?
Yeah. So, see, the thing is that our idea is that you can remember this curve, right? This is your frequency versus log R by Q curve. Okay. And whatever you have on the left-hand side of this line, this vertical axis, whatever you have on that side, that is the failure, because on the left-hand side, your ln R by Q is less than 0. That means your R by Q is less than 1. That means your R is less than Q. So on this side, you have the failure. This much is clear?
Yes, sir.
Yeah, so on this side of this axis, your ln R by Q is less than 0, or in other words, R is less than Q.
Yes, sir.
Fine. So what we want to do is, we want to, let's say I want this area to be, and this area represents the probability of failure. So I want to minimize this area. So let's say I want to say that this area should not be, area represents the probability, remember that. So let's say I say this area should be less than 1:1000. So how do I make sure I can shift? What I can do is, I cannot change the slope of this curve. So I cannot make, instead of a flatter curve, I cannot make it a steeper curve. This I can't do, right? Because that depends on what kind of materials I'm using, and I don't have that option. But still, there is something I can do to reduce this area. What can I do? I can shift the entire curve this way. So if I force this curve to move this way, yeah, it's becoming a bit, the slide is becoming very cluttery now with so many doodling by me. Okay, I hope you are still able to follow. So if I can somehow shift this curve this way, then the area of the under the curve that is on the left hand side of this axis will reduce.
Yes.
Okay, and how do I do that? How do I measure it? Of course, I can shift it. By shifting it basically means that I have to increase the value of ln r by q. ln r by q mean. I have to increase that value. That means r mean has to be, I have to increase the value of r mean with respect to q mean.
Yes.
Right? Or r median with respect to q median. That's what I have to do. Right? And how do I measure that? I can, so basically what I'm doing is I'm producing a factor beta, which represents a factor. So let's say this sigma is the function of this distribution. So I can't change sigma because sigma depends on how steep this curve is. Fine? Or what is the shape of this curve. So sigma I cannot change. What I can change is I can move this point or this point in this direction. And when I move it, the distance between here and here, I'm measuring it as beta times that sigma. Okay, so beta is the made up coefficient I have come up with. And if I fix the value of beta, for a given value of beta, my area on this side will be fixed. So if I pick a value of beta that is equal to, if I pick a value of beta that is equal to 3, let's say 3.09, then the area on the left hand side of that axis becomes 1 divided by 1000.
Yes.
Okay.
Yes.
And if I keep increasing my beta further and further, that means beta is basically beta sigma is this distance. If sigma is this distance, beta sigma is this distance, and beta is that factor, that is the ratio of this distance to this distance. So if I keep increasing my beta, I'm pushing this curve further and further in this direction, and I'm reducing the area on the left hand side. Is that clear?
Yes, sir.
Yeah. You can ask me later if you have more questions. Anybody else? Okay, I don't think I'll be able to start discussion on tension members today then, because we are already at 5:12. Okay, so quickly going over this one. So there are two approaches. Up to 2007 version, we had only the allowable stress method in the IS 800. In 2007, the IS 800 was revised and we introduced LRFD or LSD, limit state method. Okay, the fundamental difference between the two approaches is, as I had mentioned, in the ASD method, we didn't have any load factors. We only had load estimates. So you would calculate the load, live load, dead load, wind load, based on the respective codes which provide you the load values. And this is the Q value. And R, of course, it understood that there was a distribution. Okay, so R will be distributed like this, and we had to make sure this is R mean, and this might be your real R, or it may be anywhere, maybe here or here. So, but if your R real is this one, then you have to make sure that R real is more than Q. And how do you make sure? By pushing R mean or R median this way, so far enough so that your most probable R real is still greater than Q. Okay, and for that, so you didn't have any Q factors. There was no distribution for Q that was considered. You only considered the factor for R. So this did not exist. In as a consequence, what happened was that all different types of loads, let's say dead load or wind load, for all of them, we were considering the same kind of load factors. Okay, but what happened in this code is that they appreciated that the different loads have different levels of scatter or different levels of unpredictability. So if a load is more unpredictable, it will have a flatter curve. If a load is more predictable, then it will have a steeper curve. Fine. Okay. So they understood that different types of loads will have different type of their own sigmas or standard deviation. So they said, okay, let's introduce two factors. And that's how the two factors of gamma F and gamma came in. Earlier, you had only one factor of safety of, let's say, 0.6, 0.6, and so on for tension yields for different types of failures, which were only the resistance factors and there were no load factors. So basically what you are doing, you are making sure that your R mean was far enough from Q. And even now you are making sure of that. Even now you are making sure that your Rm is far enough from Qm. Okay, but now you can do two ways, by applying one factor of safety here and another factor of safety here. So you have one factor of safety for Q, one factor of safety for R, and that is because the two distributions or two levels of uncertainty, one at the load level, another one at the strength level, both of them, or resistance level, both of them are being considered. Okay, so these load factors are available in the in tables 4 and 5. So we will quickly look at okay, now one thing, I'm sure you are all familiar with the load factor values, right? So for load factor, you have seen this table in IS 800.
Yes, sir.
Table 5, table 4 rather. Yeah, so you can see this table here. So these are the different types of load factors. For dead load plus live load, let's say let's take a combination of dead load plus live load plus accidental load. Here, this one. So for plus crane load, let's say, if the crane load does not exist, you just take dead load plus live load. Load factors of safety are 1.5 and 1.5. And if there are two types of live loads acting, then the second live load, that is smaller one, you will take only 1.05. That is for limit state of strength. For limit state of serviceability, you take 1 and 1. That is very similar to what you are doing in the working stress method. Okay, so you are taking one factor of safety from the load side, and then also you take one factor of safety from the resistance side. These are given in table number 5. So resistance, yielding, buckling, you take 1.1. Now, just curious case, let's say you have a tension member which is going to fail under yielding and under the dead loads. So one factor of safety is coming from the dead load, that is 1.5. Okay, and one factor of safety is coming from the yielding, that is 1.1. What will be the total factor of safety? Somebody? How much will it be?
1.6.
1.65, right? 1.1 multiplied by 1.5. So 1.65 is the total factor of safety. 1 divided by 1.565 is how much?
0.60, 60%.
Divided by
0.67, sir.
0.60. Okay. Now you look at earlier version or ASD version of IS 800. What was the factor of safety for tension yielding? It is not really factor of safety. It is basically 1 divided by 0.6, you have to say. That is the factor of safety. So that was 0.6.
0.6.
0.6. And that's what exactly now you have. So earlier you were not using your factor of 1.5 with the dead load that you are using now, but you are using a factor of 0.6 with the resistance directly. Okay. But the two factors are basically still the same. So earlier it was basically, if I can write 1.65. Yeah. And presently what you have is this 1.5 from here. And then what you have is, let's say you're talking about yielding. So you have 1.1 from here, right? So 1.1 multiplied by 1.5 is also 1.65, which is exactly matching with the older provisions. So the way they have come up with these factors of 1.5, etc., is not necessarily purely based on science or actual observations of the load distribution or the distribution of the distribution probability distribution of these loads, etc. What they have tried is to make sure that the designs which were safe based on the earlier version of IS 800 are still safe. So they have come up with these factors accordingly. But in future, these factors can be revised if we have more data available. So for example, keeping a factor of 1.5 with dead load does not make a lot of sense. They kept it in this present version, but in future, probably they should try to reconsider it. In the US, for example, if you take a typical load combination, so then what you have is 1.2 times the dead load and 1.6 times the live load. LR is the roof live load, okay, or this live load. And F stands for load due to fluids. Okay, that's it. So since live load is harder to predict, you have 1.6 factor, and dead load is easier to predict, you have 1.2 factor. In the Euro code, if you see, you have a smaller factor for gravity loads, which are dead loads, versus imposed loads. So imposed loads, you have a factor of 1.5, but dead loads, you have a factor of 1.35, smaller factor. Because why do you have a smaller factor for certain loads?
Higher confidence in predicting.
Exactly. So what it matters is that what is the level of scatter the real data may have. So the G value that you are taking is the expected value that you estimated, but the real values may be not very different from your estimated value. Then you take a smaller factor. But if the real values can be very, very different from your estimation, then you take a larger factor. Fine. In the Indian code, still we have that. And plus, similarly, when we look at the resistance factors, now our resistance factors are very similar to the international level. So if you see American code, this is AISC 360, that is American code, LRFD design. And this is our LSD design as per Indian code, which are basically the two different names for almost the same thing. So here you can see that for tension yield, they have a factor of 1.11. We have a factor of 1.10, almost the same. Buckling, compression buckling, they have a factor of 1.11. We have a 1.10. For fracture, ultimate stress, okay, we have 1.25 and they have 1.33. Again, not very different still. Yeah. So now you can see that we are, at least in the resistance side, we are very close to the international practices. On the load side, we are slightly off, especially with the treatment of dead load. We are still using very large factors of safety with the dead load that can be modified and brought closer to the international standards. Okay, that's my opinion. But if you're designing something in India, you have to use the codes that are the numbers that are given in the code. Okay, fine. So with this, I think I concluded the introductory lecture. That is 3 lectures I have taken so far. Any questions? I don't think I have time today to go into the tension member design, so I'll probably stop here now. If you have any questions, I can answer them.
But in the Euro code 1, I mean, the wind load is predicted with 0.75. So why?
Okay, I mean, I have not designed any structures using the Eurocode. Of course, there must be some reason for that. Yeah, so like, why have they taken 0.75 when they are taking the full wind live load? Sometimes what happens is that full live load with the full wind load is very unlikely. So that can be one explanation. But yeah, I don't. That is understandable, but I don't know exactly whether that was the explanation. Many codes do that kind of a treatment. When you take one of these earthquake loads, so for example, when we are designing for earthquake loads, often we used to take half of the live load that accompanies the earthquake load. Yeah, because even in the Indian code, if here you can see when you are designing for the earthquake load, can you see here?
Yes, sir. Yes.
So either you are taking this is earthquake load, right? EL is earthquake load. So that is 0.6 times 0.6 earthquake load when you are taking the live load as 1.2. Or I think there was another combination. Yeah, so when you take the full wind load or earthquake load, then you don't take any live load.
Yes, sir. Yes.
When you take 1.5 times the wind load, then you don't take any live load, because the probability of very heavy earthquake hitting when you have very heavy live load acting on the building is very, very low.
Yes, sir, I got the point. Thank you, sir.
Also, this concept of 2 different types of live load is also that these are the 2 live loads which, let's say you have these 2 live loads, this one and this one, right? So 2 live loads are given. These 2 live loads have to be the kind which don't come together by nature. Okay, so say for example, you cannot say that see, live load is furniture and live load is also people walking in. So you cannot say that people and furniture live load, one can be the leading and the other can be accompanying, because furniture is used by people, right? So when you have more people, you are more likely to have more furniture also. So then you have to use same factor of safety for them, considering them as both leading. But you have, let's say, 2 different types of live loads which are not by nature supposed to be simultaneous. One example can be, let's say, on a building, on a particular floor, you have some machinery. And on a different floor, you have an assembly room. Okay, and that machinery is not necessarily air conditioning machinery, because that air conditioning is also associated with people's presence. So it should not be something that is attached with the people, or that has some connection with the people's presence there. So you have, let's say, some other type of a machinery, some mill or something, I don't know. Where would that situation arise? I can't think of. But let's say you have some such situation where some machinery which is completely independent of those people there. Now, the probability of that machinery operating its full capacity and all those people also being present, which don't always have to be there at their full capacity at the same time, is very unlikely. So in that case, what you can do is, for the leading, which one is, by leading it basically means the heavier one, or that the one that has more significant effect on the structural members. For that, you take a factor of safety of 1.5, but for the other one, you take a factor of safety of only 1.05. Okay. So likewise, you have some advantages, or some concession is given. Okay. Similarly, there is fire load also. Fire load, the code does not deal with it here in this common chapter, but it talks about that in the separate chapter. There is a separate chapter in IS 800 on fire loads. There it talks about it. All right, folks. Any other questions? Very few of you are asking questions regularly. Kelvin?
Yes, sir. I'm fairly clear.
You're okay? You are able to follow what we are teaching?
Yes.
Yeah. How do you like our curriculum, syllabus, the style of teaching, etc., in comparison to what you are used to?
Well, it's a bit difficult that I've had online classes before, but I'm coping okay with it.
Okay. Let me know if you have any doubts, any issues. Yeah.
Sure, no problem.
Okay. And okay, so almost all of you have broadband connection at homes, or most of you are working with 4G or something?
No, sir, broadband.
Broadband. I can see some of you are, say, Vishal Naik. Where are you from, Vishal?
Sir?
Vishal, where are you from?
I am from Odisha, sir.
Odisha, and you are at your home right now, right?
Yes, sir.
So you have good internet connection at home?
Yes, sir.
Okay. Dipsy?
Yes, sir.
Yeah, you also have good internet connection?
Yeah.
See, if
Yes, sir.
okay, so if anybody is having issues with internet or something, and you want me to explain something later on again, you let me know. We'll try to find out some way to get through to you. Yeah, don't be shy. These are not usual times, so we will try to accommodate your requirements as much as we can. Yeah.
Okay,
Okay,
sir.
folks. All right, chalo.
Okay, sir.
So yeah, this was the third lecture, right? So yeah, I have to speed up a little bit. So, compression members is the biggest chapter, heaviest chapter. That's where some theory is also. So all of you are almost all of you are taking or have taken the course on advanced structural mechanics, right?
Yes, sir.
Dr. Mahendra.
Yes, sir.
So has he started teaching column buckling already? Not yet, sir. He started teaching column buckling, no? Flexural buckling you are familiar with now. Right? Elastic flexural buckling? Yes or no?
So today was the first class of column buckling, so we dealt with the Euler buckling problems.
Okay, fine. So that is, so yeah, there is plenty of time before we go into compression members. You would have enough background so that we won't have an issue. Fine. All right, chalo. Thank you.
Thank you,
Thank you,
sir.
sir.
Thank you, 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 sir. Thank you, sir.
Yeah. Bye-bye. Thank you.